Hi, this is Kevin. Today I'll talk about the Ford Fulkerson algorithm. Hopefully this will help me, and maybe others, learn and remember this concept better. Well, let's get started.
Suppose you had to distribute water from a source to a target place, and you had weigh stations to help direct the water and pipes of different capacities for the water. How would you determine which pipes would maximize the flow of water to the target? Well, one way of doing it is with the Ford Fulkerson algorithm. The algorithm takes a directed graph and determines the maximum flow. I will demonstrate the algorithm on these three examples. Let's start with example number 1. Suppose you have a simple graph like this. There's a source S and a target T. The edge in between has a capacity of 10 units. However, only 5 units of water is flowing through it. Even if the answer is simple, let's use the algorithm to find the maximum flow. Step 1. Make all of the flows in the flow graph 0. So I took the original graph with its single edge that has a capacity of 10 and made the flow 0. Next, create a residual graph. This is like a scratch pad or a temporary graph that helps make things clearer. First, look at the residual graph. What's the maximum amount of water I can push from S to T? 10. So in the path from S to T, increase the flow to 10 in the flow graph. Now create two edges in the residual graph, the forward edge and the backward edge. The forward edge in the residual graph shows how much more flow we can push from S to T. The backward edge shows how much flow we can take back. Since we cannot push any more units of water from S to T, the forward edge is 0. We can undo 10 units of water from S to T, so the backward edge is 10. Take a look at the residual graph again. Is there any path from S to T? Nope. So we're done. So if you look at the flow graph, the amount of flow entering T is 10, which is the same amount leaving S. This means that this is the maximum amount of flow the system can handle. Another way to look at it is to separate the graph with something called a cut. So a cut is a group of edges that separates the graph into two parts. Note that the smallest amount of water that flows from S to T through all the cuts is also the maximum amount of water that can flow through this graph, because the cut identifies the edges that are the bottleneck of the system. You can't see it well in this example, so let's move on to example number 2. So for the second example, we have a new flow graph. And here we create a residual graph just like before. Take a look at the residual graph. Is there a path from S to T? Yes, let's pick S, A, B, T. The bottleneck is 1 because the minimum edge from S, A, B, T is 1. So update the flow graph and push 1 unit of water from S to A to B to T. Then update the residual graph and add the forward and backward edges. Again, the green arrows are the forward edges, which show how much more water can be pushed through the edge. Red arrows show how much more can be taken back. Well, let's continue and look at the residual graph. Are there any more paths from S to T? Actually, we could pick SBAT because we can traverse the red arrows. In this case, what is the bottleneck of SBAT? 1. So we update the flow graph of SBAT and push a flow of 1 more unit of water. Then update the residual graph. Well, is there a path from S to T? You could pick SABT again, and after updating the flow graph and the residual graph, you are right back where you started. If you keep going down this route, you could pick SABT, SBAT over and over again for a total of 400 times, which is kind of inefficient. So this illustrates that you need care in picking the right augmenting path. Let's start over. Let's suppose we pick the path with the largest capacity. Let's pick SAT. What's the bottleneck, or the maximum flow you can push through this path? 200. So you update the flow graph and push 200 through SAT. And then update the residual graph. Now, is there another path from S to T? Yes, SBT. Update the flow graph and push 200 through SBT. Update the residual graph. And now look at the residual graph. Is there any path from S to T? No. So we're done. Since the amount of water that can go into T is 200 plus 200 equals 400, the maximum value of this flow graph is 400. To find the minimum cut, look at the flow graph. The minimum cut are the vertices that cannot be reached by the S node. So A and B cannot be reached from S. So the minimum cut is this. We've divided the graph into two disjoint sets. The cut is the minimum value of edges from S to T, and it is also the maximum flow value from S to T. So it fits. Now for example number 3. Let's take a look at this flow graph from Chapter 7 of the book Kleinberg-Tardos. I will attempt, hopefully, to get this right. As you can see, this flow graph already has some flows filled in. The question is, what is the flow value of this graph? Well, look at all the flows going into T, the target. 5 plus 8 plus 5 is 18. So the flow value of this graph is 18. Now the question is this the maximum flow for this graph? First, construct the residual graph. Is there a flow from S to T? Yes, S, B, C, D, T. Here, let me only show the arrows we're traversing. There. So the bottleneck of this path is 3. So push only 3 through this path. Update the flow graph. Note that CD is a backward edge, so we remove 3 from the flow. Now update the residual graph, and we're done. The graph now has the maximum flow of water through it. It has a max flow of 21 because 5 plus 8 plus 8 is 21. Find the ST cut. Let's ask, which vertices can S still push flow to? S can only push flow to B, so those two nodes are one set. The rest of the nodes, A, C, D, and T, belong to another set. Notice that the capacity of the flows going out of the first set equals 21.
Well, that's all I have for the Ford Fulkerson algorithm. Hopefully I didn't make a mistake in any of my graphs. Regardless, I hope this is helpful. Anyway, I hope you had a good day. Remember to please like and subscribe my channel. Thank you very much for watching, and I'll see you in the next video.